All right, thank you very much for the introduction. Today, I'll be presenting Niijima, an optimizing compiler for efficient multilingual data parallel pipelines, in particular, Microsoft Scope pipeline. This is John work with a group of folks from Microsoft Research Rise Group, Margus, Mike, Madan, Todd, Ben, as well as folks from Microsoft Scope team, including Huan and Haibo. And the work was done when I visited Microsoft Research a couple years ago as a visiting researcher. So, as the name of this session suggests, data is everywhere. And so one of the recent trends we can clearly observe in the big data community is that modern analytical pipelines are becoming increasingly multilingual and heterogeneous. A good example of this is Microsoft Scope and Cosmos, which combines SQL with C#-based user-defined functions. Similarly, Spark SQL allows SQL developers to easily incorporate user-defined functions written in one of the 4 languages, Java, Scala, Python, or R. The benefit of including multilingual components into the same system is obvious. So developers get to choose the languages they're familiar with to develop data processing logic, regardless of the languages in which the system is developed. However, efficiently implementing such a multilingual pipeline is particularly challenging due to 2 major problems. The first problem here is data transfer across multilingual components into the system. So data transfer in a multilingual pipeline is very much like communication between the islands, isolated notion here. So in this case, you can think of each island here as a particular runtime for executing a software component. So transportation between islands can only be done through those slow-moving cargo ships. So for example, in order for the .NET runtime to communicate with the Java runtime, .NET objects have to be first serialized into native bytes before those bytes can be loaded onto the ship. And when the ship arrives at the JVM island, those bytes have to be deserialized into Java objects before any processing can be done. To make it more concrete, let's look at this particular example in Microsoft Scope, which is Microsoft's major data processing system and is our optimization target. Scope is pretty much SQL-based language. The only difference here is that Scope allows developers to use C# to write user-defined functions to express imperative code that would be hard to express using relational logic. An example of this is string transformation that would be impossible to express using relational logic. So this example shows a very simple Scope program with 2 lines of code where SQL keywords are highlighted in blue and the C# computations are shown in red. The first statement basically extracts a structured data set with 2 columns, A and B, from this local file using default extractor, which is a C# function provided by Scope library. When the data flows from the first statement to the second statement performs filtering first, using this where clause by calling function start with on the string column B. For the rows that survive this filtering, we call another C# function T on column A and turning it into another column C. Right? Although the logic here appears simple, their implementations can be very complicated. So first, the Scope compiler transformed relational logic into pure native C++ programs for efficiency, while the C# functions invoked the program will remain C# in the generated code that relies on a .NET runtime to execute. So eventually, those statements get compiled down into a DAG-like Cosmos execution plan for execution on a Cosmos cluster. This example, the picture here shows exactly an example Cosmos execution plan with 2 vertices corresponding to these 2 statements. Recall that the relational logic, including extraction and projection, will all get compiled down into native programs. However, in order to invoke C# functions like default extractor, billions of data items have to be deserialized into .NET objects. And after the function returns, the results have to be serialized back to bytes before those bytes can flow into the second vertex to call its relational logic. And inside the second vertex, those bytes have to be deserialized back to objects in order to call those functions T and start with, and so on and so forth. Over a set of micro benchmarks, we observed that close to 33% of the execution time is spent on serialization deserialization, which is a very high cost for any production system. The second major problem here is the lack of effective optimizations. In particular, the language barrier prevents compiler optimizations from effectively going across the language boundary to optimize away inefficiencies that scatter all over the program. So here's a concrete example, which is derived from the previous example. In the first statement, we call this function toUpper, transforming every single string in column B into uppercase form in column C. And the second statement, there's another function, myTransform is invoked, transforming column from C to D. So if you look at this example for a minute, you can ask questions like, if you perform the filtering at the end, why do we have to call toUpper on every single row in column B, right? So if a row will be filtered out later, all the transformation effort done in the first statement will be completely wasted. This is exactly what this picture shows. However, this is not a new problem. This is an old problem that's been around for a decade, right? It's a typical example of a query inefficiencies that can be effectively optimized away by techniques such as predicate pushdown. So what makes it difficult here is the language barrier. It's a mix of languages. Right? A typical query optimizer only recognizes the semantics of relational algebra. It doesn't understand the semantics of imperative code, like C#, and hence cannot reason about C# functions. So before deciding which direction to go, we had a lot of meetings and communication with the product team. Our goal there was very clear in the beginning, which is whatever we implement, we want to implement them inside the production system so that they can perform optimizations for thousands of production scripts running every day inside Microsoft clusters. Publication was just a secondary goal. There's another non-technical aspect here is that we want to do things in a very careful way so that the product team is willing to cooperate. So for example, we cannot touch the runtime and any critical component on which their development depends. Otherwise, they wouldn't be happy. So these very goals dictate zero user involvement, 100% soundness, and a non-intrusive approach. So how do we go about optimizing? So we developed this approach called Niijima, which merges islands by performing source-to-source translation over the source code of scope programs. Niijima is the name of Japanese volcanic island that gets merged with another island by lava in the year of 2013. So Niijima performs two major motion tasks, consolidate and pull. So the first task, consolidate. The goal is to move together C# function calls that used to scatter all of the SQL programs into a small number of SQL statements so that the number of Cosmos vertices that require .NET runtime can be reduced, and hence the reduction of serialization and deserialization. The second major task tries to pull predicates at the source code level, which enables early filtering of data. Niijima performs these two tasks in an iterative manner until a fixed point is reached. An important thing that Niijima doesn't do is to mess around C# code that often has a very complicated logic and a pointer usage. So transformations there are very difficult to make completely sound. To make it concrete, let's look at this scope example that has 4 different C# computations. After Niijima transformation, the program looks like that. There are a few things you can observe from the optimizations, right? The first thing you can observe is that the two function calls, a.m, c.n, get consolidated into c.m.n from the second statement into the third statement by performing function composition, right? Assuming that mn are pure side effect free functions, which is usually a requirement for big data processing. This shows an example of computation consolidation. As a result, the second statement there is completely C# free that you can see. The second observation you can make from here is that this filter that used to be associated with the second statement now gets put up to the first statement and becomes a having clause there. This is an example of predicate pooling. The benefits are obvious. Computation consolidation reduces the number of SQL statements that have C# computations, and hence the Cosmos computation, the Cosmos vertices that require .NET runtime also gets reduced. And this reduces ultimately the amount of serialization and deserialization when data flows into a vertex. And of course, predicate pooling enables earlier filtering of the data and hence reduce the amount of computation and shuffling. If you look at this example for a little bit longer, you might start asking questions. Are these optimizations really needed? It seems like some of the problems that we care about here can already be solved by existing techniques. So for example, can we use operator fusion to fuse operators so that at least the inter-operator communication and serialization can be completely saved? Or we might be able to write some of the pattern matching rules as has already been done by Catalyst compiler in Spark SQL so that the compiler can help us find suspicious patterns and replace those patterns with more performant code. Another question you might ask is that, hasn't predicate pooling been done already? My short answer to this question is that although those existing techniques might work for this simple program, they typically do not work for large-scale production scripts that have more than 1,000 lines of code and involve tables with thousands of columns. As the next step, I'll give you a more realistic example with a production script to show you the real value of Niijima optimizations. So this piece of code shows a simplified version of a bin service that runs every day inside Microsoft. So although the logic here appears very complicated, the data flow is very simple. The data flow graph is showing at the bottom. So column T first gets transformed by calling this function to lower to dat.t, where dat is the name of table, T is the name of column. And then dat.t flows into 11 disjoint select statements, each with a different filtering condition, count 1 all the way to count 11. The results from those 11 select statements get combined with a union statement into a.t, which is subsequently transformed into b.time by calling this function string to time, which effectively turns strings into time objects. Eventually, when data comes into the last statement performs very strict filtering by matching the date field in each time object with a specific date, which is the midnight of April 13th, 2018. So if you look at this example for like 5 minutes, I'm pretty sure that most of you can easily identify that the last statement has a problem. Particularly the problem is with the filter there, right? If you perform filtering at the end, why don't you do this earlier? Can you move this to one of the earlier statements so that you can reduce the amount of computations? Well, the answer to this question is both yes and no. Yes, in the sense that it's possible to do, and no in the sense that if you carefully inspect the code, you can see a dependence between string to time computation in the third statement and that filter. Because string to time computes time from column T, which will be used by the filter. Right? There's a data flow constraint there. How does Niijima solve the problem? So recall that we have two optimizations, consolidation and predicate pooling. At the first step, Niijima performs computation consolidation. In particular, if you look at these two C# computations, you check the data flow graph, and you can see that there doesn't exist another computation sitting in the middle. That basically means that these two computations can be perfectly consolidated. So as the first step, Niijima consolidates these two computations by performing function composition. So in the third statement, we don't need that C# computation. We only need column T there, right? The animation here shows the effect of the computation consolidation. As a result, this reduced the number of data flow vertices that require .NET operators and enhance the serialization and deserialization. What is more important here is that at this moment, if you look at this filter again, you can find that that C# computation string to time that used to block the way for us to pull this computation now gets cleared so that Niijima can move the computation up to each of the 11 select statements and combine the logic with the existing conditions. You can clearly see from the example that consolidation and predicate pooling pave the way for each other, right? So they work very much like the traditional compiler optimizations, which pave the way for each other in the traditional compiler setting. By performing these two optimizations in an iterative manner, we ended up achieving a 2.9 times speed up for this bin service that runs every day inside Microsoft. So how do we do this? We develop a compiler that transform program into a set of micro-transformers, which are our intermediate representation. From there, we build a dependence graph. And then optimizations are formulated as graph reachability problems over the dependence graph with a very complex set of very complex rules. To evaluate, we picked 21 production jobs from the virtual cluster we had access to, and range job with A/B testing tool that compares automatically two versions of the runtime. The first version is the one used in production, and the second one is Niijima. And overall, Niijima was able to reduce the end-to-end latency by 24%. For 3 jobs, we saw a large speed up of 1.7 times, 2.9 times, and 3.3 times. For a set of 13 jobs, the improvement is larger than 10%, while for the remaining 4 jobs, we saw a slowdown. But the actual amount of slowdown for each job is smaller than 5%. We carefully inspected the programs and our transformations and confirmed that the slowdown cannot be the result of our transformations. So we believe it's execution noise. We also look at the contributions of individual optimizations. So the conclusion there is that by enabling each optimization alone, the performance improvement is way lower than enabling them together and running them iteratively. To conclude, this paper presents Niijima, which is an optimizing compiler that performs 100% sound and automatic optimizations. In this paper, we'll look at this particular optimization, which is code motion. However, our intermediate representation can be easily used and generalized to implement other optimizations as well. With that, I'll stop here, and I'm ready to take questions. Thank you very much.
Hi, Henry Ching from Square. Looking at your final example, it looked like you actually added the number of times you had to go into C# land. If you can go back to that slide.
Which slide? This slide?
Yeah, so it looks like you've added more calls to from binary here, and I'm wondering how much negative performance impact that actually causes, and whether there's something you can do about that.
I see. So basically, it's not the question is that it looks like this adds the amount of C# computations. So are you saying that the added computations goes into the second statement for the call to from binary? Is that what you're referring to?
Yeah, I mean, what it looks like from this depiction at least is that you have more from binaries than you had before. Like whereas in the previous version, your from binaries were only at the very end. Now you have from binaries on, 8 statements?
Right. So basically, I think the conclusion here is that the added computation here is much smaller than the gain benefit that comes from earlier filtering of data. And also, if you look at this statement, if you look at this example, the vertex that correspond to the second statement already needs to set up a .NET runtime, right? Even if you move C# computation into that vertex, the setup cost for the .NET runtime is already there. And that basically means that the data needs to be serialized and deserialized anyways, even if you don't have that added computation. So you don't add any extra cost for serialization, deserialization. Calling a few C# functions is very cheap.
I see. So you only pay that serialization once.
Right.
All right. Thank you.
Yep.
Hi, Matthew Milano from Cornell. This is very cool work. It seems that because you have to have an intermediate representation of all of these SQL statements and all of these C# statements, you have an opportunity to recognize when some SQL statements are doing work that could be done in C#, or some C# statements are doing work that could be done in SQL. Do you try to take advantage of that at all by transforming?
For this particular paper, we didn't do anything. But I think, like I said in the conclusion, that the intermediate representation can definitely be used for a much broader scope, like set of optimizations. So definitely what you talk about was one of such optimizations that we can do in the future.
Thank you.
Yeah.
Hi, Menak Ghosh from Twitter. Nice work. I have two questions actually.
Sure.
First is, how do you ensure correctness when you have joins? Because if you're doing predicate pooling,
Yep.
it's possible things can go wrong. And second is this one works with C#, but when you have multiple runtime environments, which you said initially, how does that generalize?
Right. So the first question is, how do we deal with join? So the short answer to this question is that we definitely, our intermediate representation has considered join, and then we basically, if you look at the format of microtransformers, we do have a clause called the shuffling. So basically, shuffling can be the result of the join, right? So we do have a modeling for join, and then we have a way of optimizing the IR, considering all those complicated constructs in SQL. You can read the paper, or we can talk offline. You know, the second question is, how do we generalize the C#? So the current paper only deals with C#. I think the optimizations can easily be generalized to any setting where you have a mix of SQL and imperative programs. Even if the imperative programs are written in Java or Python or any other languages, as long as you have a different compiler that translates the language into the right IR, the IR is general enough to be able to express all different constructs. Right?
Thank you.
Thank you.
All right, let's thank the speaker again.
Thank you.